Welcome back to Neural Intel. Today we're diving deep into some really interesting research focused on boosting how language models actually reason.
That's right. We're zeroing in on the technical core, the nuts and bolts of a new approach.
Exactly. For you, the learner listening in, we know you want to get the important technical stuff quickly without, getting lost in the weeds. This deep dive aims to cut right through.
And we've got the paper right here, DISCIPL, Self-Driving Inference with Language Model Probabilistic Programs. It's up on ArcHip if you want the full details. We'll link it on the webpage mentioned in the bio. But yeah, our job today is to unpack it for you.
Okay, so the paper starts with this kind of intriguing observation. You've got these incredibly powerful language models, right? They ace complex stuff, but then sometimes they stumble on tasks that seem, well, almost basic.
It's this weird inconsistency, things like counting accurately or, following simple rules within the text they generate. They call it jagged intelligence.
Jagged intelligence, I like that. It's like they can write a symphony but can't tie their shoes sometimes.
Pretty much. And this jaggedness, it really highlights why we need better, more deliberate ways for these models to think. Especially during inference, that's when they're actually doing the task, generating the output.
Right, so what are the current ways people try to handle this? The paper touches on existing methods,
Well, one big one is chain of thought. You see it a lot. The model kind of thinks out loud, showing its steps.
which is flexible,
Right.
definitely, but the paper argues it's not always efficient, right? It can be slow, uses a lot of compute.
Exactly. Slow, costly, and sometimes the reasoning path it takes isn't even, optimal or correct.
Then there are other ways, more structured.
Yeah, things like tree search, exploring different possibilities, or techniques like sequential Monte Carlo. These can be faster, sometimes run things in parallel.
But they have their own issues.
The main drawback often is needing predefined components. You might need specific ways to score intermediate steps or verify the final answer, and that often has to be custom built for each type of problem. Makes them less general, harder to just apply anywhere.
Okay, so that sets the stage perfectly for DISCIPL. Distributional constraints by inference programming with language models? Big name.
Yes, disciple. And the core idea is pretty radical, really.
Which is?
Instead of us telling the model exactly how to reason step by step for every new problem, Disciple lets the language models themselves figure out the structure of the computation. They drive their own inference.
Okay, hang on. How does that work? You mentioned language models, plural.
Right. There are two main actors. First, you have a planner LM. Think of it as the strategist, the architect.
Okay, the planner.
You give it the task, it looks at it, maybe considers past errors if available, and then it generates a plan. But it's more than just a description.
It's like actual code.
Pretty much.
Yeah.
It generates an inference program, a specific set of instructions tailored for that task.
And who runs this program?
That's the second LM, the follower LM. The inference program tells the follower exactly what to do. Maybe generate some text here, maybe calculate the probability of this word there, check this constraint.
So the planner writes the script, and the follower acts it out. Dynamically generated scripts for each task.
That's a great way to put it. It's this self-driving, program-based inference that's the key innovation.
Cool. Let's walk through the DISCIPL algorithm then, this sort of outer loop. How does it actually proceed?
Okay, step one, prompts the planner LM. Give it the task details.
Mm.
And like we said, potentially feedback from previous attempts if it messed up before.
Learning from mistakes. Nice.
Exactly. Step two, the planner chews on this and generates the inference program, the instructions.
Got it. Program generated.
Then
Yeah.
step three, an inference engine takes that program, hooks it up with a follower LM, sets a computational budget, like how much time or resources it can use, and then just runs the program.
Executes the plan. What if the program itself has a bug or something goes wrong during execution?
Good question. It's not brittle. If errors pop up, maybe the program asks for something impossible or gets stuck. Disciple can actually retry. It goes back to the planner, tells it, hey, running that program caused this specific error, and asks the planner to generate a new, hopefully corrected program.
So it can debug its own generated plans. That's
Oh.
pretty sophisticated.
It adds a layer of robustness for sure.
Okay, let's zoom in on these language model probabilistic programs. What are they made of? What do they actually look like?
They're essentially scripts that give really fine-grained commands to the follower LM. They dictate how it uses its probabilistic knowledge, either for sampling new tokens or for evaluating the likelihood of existing ones.
The paper had that example, figure 1, adding words with constraints.
Right. A stochastic addition task.
Uh-huh.
Building a sequence but having to meet certain rules. That example shows commands like observe.
There, observe. What's its function?
Observe is crucial. It's how the program enforces constraints. It basically tells the inference engine, make sure the follower LM assigns a reasonable probability to this specific word or this condition being met right now.
And if the follower thinks it's unlikely?
Then the score of that particular sequence gets penalized. If the probability is super low, that path might get called just dropped entirely from consideration.
So it steers the generation away from paths that violate the rules.
Precisely. It can encode hard constraints, violate this, score goes to 0, you're out, or softer preferences where maybe less likely paths just get downweighted. The programs use standard logic alongside these LM calls to manage the generation and scoring.
It feels like there's some deep probability theory going on underneath this. The paper mentions a mathematical view.
Yeah, they formalize it a bit. They think of these programs as building recipes for sequential inference algorithms.
Sequential inference, meaning step by step.
Right, building the output piece by piece. The goal is to sample from some target distribution, basically, the set of all valid and good answers, where the sequences that consistently scored well during generation have the highest probability of being the final output.
Okay, and there was a step function, sigma.
Sigma is the mathematical description of one step. Given the text generated so far, let's call it S, sigma tells you the distribution over possible next pieces of text, and importantly, how the score changes for each possibility based on the program's rules.
So it maps the current state to the next possible states and their scores.
Exactly. And the overall probability of ending up with a final sequence S is related to the product of all those score updates you encountered along the way to generate it.
Makes sense. So how does this whole DISCIPL framework stack up against the methods we mentioned earlier, like just standard generation?
Well, standard autoregressive generation word by word can be very expensive, as we said. DISCIPL aims to be smarter by letting the planner design a potentially more efficient, task-specific procedure. It's not just blindly predicting the next token.
And compared to things like tree search or SMC?
The big difference is automation. With traditional tree search, or SMC, a human usually has to design the search strategy, the scoring function, the proposal mechanism.
Yeah.
It's manual expert work.
Whereas
DISCIPL gets the planner LM to generate that procedure automatically. That's the leap. It figures out how to search or sample for that specific problem.
that is a significant shift. The paper also briefly compares it to self-improvement methods. Is it like models, teaching models?
There's definitely a recursive feel to it, yeah. An LM generating code to control another LM. But DISCIPL's focus is very much on creating these ad hoc, temporary inference algorithms for specific tasks, giving really precise, often probabilistic, token-level control. It's less about permanently retraining the follower.
Gotcha. And its connection to constraint generation research seems like a natural fit.
Oh, absolutely. It's a powerful new tool for constraint generation. A lot of prior work focused on specific decoding algorithms for certain types of constraints or maybe training separate guidance models.
But DISCIPL is more general.
It seems to be. The idea is that the planner can, in principle, generate a program to handle many different kinds of complex, even compositional constraints by encoding them directly into the inference logic.
You mentioned sequential Monte Carlo SMC again. How exactly does DISCIPL leverage that?
So SMC is fundamentally a framework for adaptive search. You maintain a collection of possibilities, or particles, and you update them, resample them, based on how well they seem to be doing. It's great for exploring complex spaces,
Okay.
but applying SMC to a new problem usually takes serious engineering effort. You have to define how to propose new steps, how to score things, when to resample.
And DISCIPL automates this part.
That's the claim. The planner LM can generate an inference program that implements an SMC-like procedure tailored for the task at hand. It figures out the proposal, scoring, and resampling logic needed.
Wow. Automating the setup of a complex inference technique like SMC.
Yeah, it's pretty ambitious.
So what are the key commands or building blocks these inference programs use? You mentioned observe. What else?
There's sample, which is the basic ask the follower LM to generate something command. We covered observe for constraints. Then there's hint. Hint lets the program dynamically update the follower's prompt or context with information learned during the inference process. Like, okay, we've already placed 3 A's. Remember that when generating the next word. It keeps the follower informed.
Dynamic context updates.
Yeah.
Useful. Anything else?
They also use token masking quite a bit.
Yeah.
That's where the program directly restricts the vocabulary the follower can even choose from at a given step, like forcing it to pick a digit or a specific type of word, sometimes combined with importance waiting to correct for the bias introduced by the masking.
Okay, quite a toolbox for the planner. So the million-dollar question, does it actually work? How did it do in the experiments?
They ran evaluations on two benchmark sets, one called Collie, focused specifically on constrained generation tasks, things like anagrams, specific word counts, character positions,
Right.
and another called PZOES, which has more sort of naturalistic generation tasks that still require some underlying reasoning or constraint following.
And the metrics, how did they measure success?
They looked mainly at pass at one, basically. Does the single best answer it produces actually meet all the constraints? Is it valid? And also coherency. Does the output make sense? Is it fluent English?
Makes sense. Who are the baselines? What did they compare DISCIPL against?
They had several. One was just using the Planner LM directly, TPT-4o in their setup, to try and solve the task without the structured inference. Another was using only the Follower LM, a smaller llama model, basically standard generation. And they also compared against a strong, dedicated reasoning model called O1.
Okay, and the results, did DISCIPL pull ahead?
Yeah, the results are pretty strong. DISCIPL significantly outperformed the follower-only baseline pretty much across the board. It could handle constraints like character counting or word positioning that the base llama model just couldn't manage reliably.
That's a clear win for the structured approach. How did it do against the bigger models?
On the Kali sentence tasks, which are quite structured, DISCIPL actually got pretty close to the performance of the specialized reasoning model O1, which is impressive given that DISCIPL is generating a strategy on the fly.
And on the puzzle LES tasks, the more natural ones.
There, DISCIPL generally did better than both the planner-only and follower-only methods. Interestingly, though, they also tested DISCIPL using human-written inference programs for those complex puzzle LAS tasks, and those handcrafted programs still performed the best.
Ah, so human ingenuity in designing the program still wins for the really tricky stuff, but the planner's auto-generated programs are a big step up from the baselines.
Exactly. It shows the potential, but also that there's room for the planner to get even better at strategy generation.
Do they see any benefit from using SMC specifically within DISCIPL compared to simpler sampling?
Yes, they did. They found that using SMC often resulted in higher coherency scores compared to a simpler technique like importance sampling, IS, even if the validity pass at 1 was similar.
Why would that be?
The thinking is that the resampling step in SMC helps prune away candidates that might technically satisfy the rules but sound weird or unnatural. IS might keep those low-quality but valid options around longer. So SMC gives you answers that are both correct and sound better.
That's a subtle but important advantage. What about the check functions the planner could generate? Could it reliably verify its own answers?
Apparently, yes. They found that the auto-generated check methods agreed very closely with the gold standard human-written verifiers for the tasks. So the planner isn't just good at planning the reasoning, it's also pretty good at planning how to check the reasoning.
Okay, DISCIPL looks really promising, but no research is perfect. What limitations or future directions did the authors point out?
They were quite upfront about that. One big area is generalization. How well does this work on other kinds of constraints, like mathematical reasoning, or constraints that are soft, more like guidelines than hard rules? That needs more exploration.
Makes sense. What else?
They also suggest trying other inference algorithms within the DISCIPL framework. They mostly focused on sequential, SMC-like approaches. But could the planner generate programs that implement, say, backtracking search or iterative refinement where you edit the output? Lots of possibilities there.
Any practical hurdles they hit during the experiments? Things that didn't always work smoothly?
They did mention a few things. Sometimes the generated programs created invalid token masks, basically painting themselves into a corner where no word was allowed next.
Weeks.
Yeah. And also occasional timeouts. If the generated program didn't have a clear stopping condition or got into some kind of loop, standard programming bugs, essentially, but generated by an AI.
Right. The usual challenges just in a new context, so future work would try to address these.
Definitely. A key idea is improving the feedback loop to the planner. Right now, it gets fairly simple error messages. If it could get richer feedback about why an inference attempt failed or succeeded, it could potentially learn to write much better, more robust programs over time.
Okay, let's zoom out and wrap up for the learner. DISCIPL is clearly a technically sophisticated way to try and make LM reasoning more dependable, more adaptable.
Absolutely. The really big takeaway, I think, is this shift towards models designing their own reasoning strategies at the code level, dynamically, not just following fixed patterns.
Yeah, this planner writing inference programs for the follower, it just unlocks a different way of thinking about problem solving for AI. It could lead to better efficiency, better accuracy on complex tasks.
And weaving in those powerful ideas from probabilistic programming and SMC, but automating their application, that's a very advanced approach to handling the uncertainty in the huge search space these models deal with.
It really feels like the potential path towards smoothing out that jagged intelligence, making AI less brilliant but flaky and more consistently reliable across different kinds of thinking.
Which leaves us with a thought for you, the listener, to mull over. How could this core concept, meta-reasoning, AI designing its own inference procedures, influence the future development of intelligence systems more broadly?
Think about where else this idea of automated strategy generation, coupled with probabilistic execution, might pop up. Could it be adapted for domains beyond language?
This deep dive gave you the technical foundations of DISCIPL. We definitely recommend checking out the paper itself if you want to go deeper into the implementation and see all the experimental details. Again, check the link on our webpage in the bio.
Thanks for diving deep with us into the technical side of DISCIPL today. We hope it's given you some valuable insights into where AI and machine learning research is heading.